All right, so this is the mini movie on Venn diagrams, and hopefully this will help with some of the Venn diagram confusion. Let's start off with just what a Venn diagram is. We start with a box which contains all possible outcomes denoted as an S. The circle will denote a subset of those events, in this case events A, so that the A circle contains all of the A events. We can have another circle that will contain all of the B events. And if we look at where they intersect, the slice that they are both a part of, we will find all of the events that are both A and B. Now we can also look at the purple shading, and this purple shading is actually all the events that are A and or B, and the set notation that goes with that will be the union. So if we're talking about A and or B, we get the union of the two. And if we're talking about A and B, where we're just talking about that slice, we get the intersection of the two. So the intersection is this upside down U, and the union is this upside down, upside U. Now let's talk about what happens if they're mutually exclusive. If they're mutually exclusive, we know that the probability of A intersected with B is actually going to be 0. Okay, and we can put a 0 in this slice right here. Now then we know that this entire area out here has to be equal to the probability of A happening, so that the circle adds up to that probability. So we put a 0.04 out here, and we put a 0.15 in here. And if we want to know what the union of the two is, we can simply add together the 0.4 and the 1.5 to get 0.55. Now, if we wanted to go ahead and figure out what the probability is outside of the circles, then what we do is start with 1, which is actually the probability that S will happen. Remember, S is all possible outcomes, so there has to be something that happens. And we're going to minus off the probabilities that we don't want, which is going to be the union of A and B. That equals the 0.55, so outside the circles is 0.45. So there you go. Now, what happens if they are not mutually exclusive? Okay, so I changed it here so that the intersection of A and B, instead of being equal to 0, is actually equal to 0.05, which means they are not mutually exclusive. Okay, now I'm going to go ahead and use the same thing. The probability of A is 0.4 and the probability of B is 0.15. Now, if we did the same thing that we did last time to get the union of the two, and we added 0.4 and 0.4 and 0.15, what would happen is we would be adding this circle and this circle, and we would actually have this slice in there twice. Let's do a Venn diagram to see what that really looks like. All right, so here are the givens. The probability of A intersected with B is 0.05, which is going to go right here in the center. The value of what goes into this circle has to be 0.4, so I put 0.35 out here so that the total equals 0.4. The total in this circle has to be 0.15, so I put a 0.1 here so that that happens. And now when we do the Venn diagram, we add together the 0.35, the 0.05, and the 0.10. And what we're going to get this time is 0.5. Now, another way to do this would be to go ahead, if we wanted to use these numbers up here, would be to go ahead and use this 0.4 plus this 0.15, and then we just have to minus off that center slice. Remember, we added it in twice, so if we just minus it once, we're back to the right value, which in this case is 0.5. This actually gives us the addition rule. The addition rule deals with unions, and it deals with adding two things together. Now, if they are not mutually exclusive, you have to make sure that you also minus off that slice. Now, if they are mutually exclusive, this term right here will be 0, and it'll be exactly the same equation that we used 2 slides ago. Now, what about if they're independent? Well, if two events are independent, then you can take the probabilities associated with both events, multiply them together, get a new value which actually tells you what the probability of both events happening is. So in this case, the probability of A times the probability of B will give us the probability of A being intersected with B. And in this case, it's 0.06. If we go ahead and do our Venn diagram, we're going to go ahead and put in our 0.06 right here. And then to make sure that this is still 0.4, this value is going to have to be 0.34. And to make sure that this value is still 0.15, this value is going to have to be 0.05. So if we're going to try to figure out the union again, we're going to add the 0.34, the 0.06, and the 0.09. And the result is 0.49. Now, what you'll notice is that if we had just added these two together, we would have gotten a different value, a much bigger value. And that's because if we take this 0.4 and this 0.45, we have to minus off that. That's the mutually exclusive part. And we get 0.49. So So that's how the independent works in terms of what we come up with for the intersection of A and B. But independent, it really gets interesting when we start thinking about conditional probability. But before we get to that, let's go ahead and do our multiplication rule. That's the other thing I've got to do down there. Now we're going to talk about conditional probability. All right, so remember in conditional probability, I'm interested in the probability that A will occur considering that B has already happened. So in the Venn diagram, this is all I care about. I don't care about any of that other stuff, so I'm just going to draw this B circle. So when we think about the successes over the number of tries, this is where we're going to have a success, where we have A and B, and this is where we have a number of tries, which is just B. So on the bottom, we have the probability of B, and on the top, we have the probability of A intersected with B. So if we put in our values, 0.06, and 0.15, and do the calculation, we get 0.4. Now what you'll notice, these were independent events, and the conditional probability is exactly equal to the regular probability. So it doesn't matter whether B happened or not, there's still the same probability that A will happen. Again, that's what it means to be independent. What happens to conditional probability when you have dependent events? Well, now we're going back to the example from before that, where the intersection was actually equal to 0.05. Now, in this case, we have 0.05 divided by 0.15, and we get 0.33, which again which, as you probably shouldn't be surprised, is not equal to probability A. It's because they're dependent events. But that just gives you an example of how that works. All right, so let's recap what we've done in this little mini movie. We've talked about Venn diagrams. We talked about the sample space S, which is the box. We talked about events A and B, for example, which are circles. We can have another event, C, which we didn't talk about in the video, but we could be there, and it would overlap in such a way that we'd be able to tell what things are in common between them. Mutually exclusive means that there are two events that don't have anything in common. Independent means that you can multiply the individual probabilities to get the intersection. It also means that the probability of A happening considering that B has already happened is going to be exactly the same as the probability all by itself. We talked a little bit about unions and intersections, where the union is actually a U and an intersection is an upside down U. But there's another little mini video that'll go in a little bit more detail about how to work with the unions and intersections and the Venn diagram. So you might want to check that out. We also recapped the multiplication rule, the addition rule, and the subtraction rule. And then finally, a little bit more about conditional probability, especially how it relates to whether or not two events are independent. So hopefully this helped to clear up some confusion about Venn diagrams. Have a great day.